morning to everyone. I am Lanya. Today I am here to give a few presentation about my project. My project title is Dynamic Behavior and Stability Analysis of Automatic Voltage Regulator with Parameter Uncertainty. Here are my team members, Ismail, Lernish, Darhas. Today we will discuss our project. Here dynamic behavior. Dynamic behavior means in power system network, maintaining voltage as constant is a very difficult task because voltage has a very close relation to power quality. So we need to install an AVR, that is automatic voltage regulator. But unfortunately, AVR can't do this solely. So we need some PID controllers. Next, we'll move to closed loop block diagram representation of AVR. Here, this is our block diagram. In this block diagram, we have amplifier, field exciter, AC generator, and voltage sensor. Here, amplifier has gain and time. K means gain, here T or tau means time. So, this is our block diagram. By using this block diagram, without any controller, we will get a waveform. Here we will take nominal parameters of this voltage sensor, amplifier, exciter, and synchronous generator. Here these are the proposed nominal values, and voltage sensor will take the minimum values, that is 1.0 and 0.01 seconds. Amplifier also 10 and 0.1, exciter also 1.0, 0.4, and generator also 1.0, 1.0 seconds. Here voltage sensor, amplifier, exciter, alternator, synchronous generator will have the proposed nominal values. By using these values in the block diagram, we'll get one waveform, and we'll take the one closed loop transfer function, that is this. Here 0.1 s plus 10 by 0.0004 s power 4 plus 0.0454 s cube plus 0.555 s square plus 1.51 s plus 11. This is our closed loop transfer function. By using this closed loop transfer function and the nominal parameters, by inserting these values in block diagram, I'll get one waveform, that is this. Without any controllers we are using, I'll get this waveform. From this I'll get a rise time, steady state error, and a peak overshoot. Okay, this is our this is from block diagram we'll get this closed loop response of AVR. Next, here we have taken the PID controller as a, because the AVR can't do this solely, so we need PID controller. In this PID controller, we have taken some techniques. Those are genetic algorithm, local unimodal sampling, water cycle algorithm, and proposed technique is Simulink design optimization. Here, genetic algorithm, local unimodal sampling, water cycle algorithm are the compared techniques. We'll compare these techniques with the proposed controller, that is SDO, Simulink design optimization technique. Next, we'll take the PID coefficients for water cycle algorithm of PID coefficients. Those are Kp equal to 0.585, Ki is 0.441, Kd is 0.2158. Next, genetic algorithm. We'll take Kp equal to 0.585, Ki equal to 0.441, Kd equal to 0.2158. And next, local unimodal sampling. Kp equal to 0.722, Ki equal to 0.3767, Kd equal to 0.1841. Simple design optimization of PID coefficients are Kp equal to 0.815, Ki is 0.563, Kd equal to 0.284. These are the PID coefficients per closed loop transfer function. Next, by using these PID coefficients, we'll find out the stability analysis. To check the AVR loop stability, we need three. Those are time domain analysis, pole zero map, and Bode plot. First, we discuss about the time domain analysis. Time domain analysis means, in this we have a block diagram, that is this. In this block diagram, we have amplifier, exciter, generator, and voltage sensor. This is our closed loop block diagram. In this closed loop block diagram, we have taken extra PID controller. Our proposed is SDO, and remaining are the compared controllers. We'll follow this. By using this block diagram, in this we have taken the PID values. Those are these. Here proportional means Kp, integral means Ki, derivative means 0.285. I have inserting these values in the PID. So now this is our block diagram. For all things, we have inserting the Kp, Ki, Kd values. After this, we'll run the program. We can check our output. This is our output. Here we have rise time, peak here rise time. This is peak overshoot and steady state error. So less rise time means more stable. Peak overshoot also. Less means more stable. So by using this, we have four controllers, different four colors. So we can see this easily in tabular column comparison table. That is, I'll show. Here we have, this is rise time, peak overshoot, settling time. This is rise time. Here all the compared controllers have more rise time, but SEO has less rise time. Next, peak overshoot also very less means it is more stable, but here water cycle algorithm are also having very less. But comparing with rise time and overshoot, we'll have SDO has less rise time. So we can say that here settling time is more. If settling time also we can compare with rise time, so we can say that SDO PID controller is best. Okay, settling time also less we need to be, but here watt cycle also less settling time. Compared to this, we have rise time is less in HDO controller, so we can say that in time domain analysis, Simlic design optimization is best controller because it can stable the system in less time compared to other controllers. Next, we'll move to pole zero map. Pole zero map means we have to find the poles and zeros in this. So this has one program. We can see that program. Wait. This is our program, pole zero map. Okay. We have the poles and zeros here. We'll see the pole zero map. This is our program. In this, we'll see the poles and zeros. The program is here. We have PID controller values for different compared controllers. Here SDO is the proposed controller genetic algorithm. Here SDO is a proposed genetic algorithm is compared water cycle algorithm also compared, LUS also compared. These are our water cycle algorithm. I'll say algorithm. Okay, this is our program. Here we have taken the numerator, denominator and poles of the closed loop. Without controller, with controller we have taken. Now we can run the program. I'll see the output. Wait. This is our program run. We'll get this. These are the poles and zeros. Okay. These are poles. Here, pole is this. These are poles and these are zeros. We have different colors. So those can identify which is SDO, which is water cycle algorithm, genetic algorithm, and local unimodal sampling. For this, we have taken a comparison table which can easily understand. So we'll see in that. This is our poles and zeros of AVR loop with controllers. Here are our poles and zeros. And these zeros means real. If the zeros are real, then the system is stable. Comparing to all, here we have SDO PID is real. So we'll say that SDO PID in poles and zeros of AVR loop with controllers is a more stable. So we can say is best controller compared to compared controllers. So we have the poles also here. We have less imaginary values as compared to remaining compared controllers. We have real values more in SDO compared to complex values. So we can say poles and zeros, our pole zero map is as comparing with other controllers, the proposed controller SDO is best. The system is more stable. Next, we want to check Bode plot. Bode plot. In Bode plot, we have gain margin and phase margin. To find this Bode plot, we need a program. So we see the program. We'll move to the program. We have the program. See here we'll keep. We'll see. Next we'll move. Okay. Now we'll check the body plot. Run the program. We'll see the body plot. This is our body plot. Here this is gain margin, this is phase margin. Phase margin is in degrees, gain margin in decibels. If it is more than 0, then we can say that it is more stable. Yeah, if more gain margin and phase margin are more values, then we can say it is more stable. So these are the four colors we can say here. By seeing this, we can say which is more stable controller. So for this, we can see in tabular column, which can be easily understood by us. So we'll move to the tabular column. This is our tabular column for classical margin comparison. In this, we have gain margin and phase margin. We'll see here the gain margin is for SDO is 24.40 decibels and phase margin is 67.9 degrees. Here dB means decibels, the gain margin is in decibels, phase margin is in degrees. Remaining compared controllers has very less comparing to SDO, less gain margin and phase margin. So we can say that SDO PID controller is best compared to other controllers to check the stability of the AVR loop. So this is about the body plot. Next, parameter uncertainty. Parameter uncertainty means here we'll take the one parameter that is maybe amplifier or voltage sensor, generator, anything, but we'll take amplifier because amplifier is a non-linear element. In non-linear, we consider the uncertainty of the amplifier parameter. Then we'll take the K amplifier and T amplifier. K means gain, T or tau means time. We'll take the maximum allowable value from its nominal values. So by using this maximum value in amplifier, okay, we can see the more stable of the amplifier. Next, the main conclusion of this project is we can say that we have taken the different controllers and compared with the proposed controller. By comparing all these, we can check the stability analysis of the controller. So by seeing all before slides, we can say that SDO is the best controller to check the stability analysis in less time as compared to other controllers. We can say that. Thank you for giving this opportunity.